So first an impression of the context we're here. This is in the Dutch delta in the Netherlands in Europe, and we're at the end of the European river Rhine. And so upstream we already have quite some impacting activities. Nonetheless, reuse in Netherlands is hardly ever considered up until now, since we have a sufficient quantity of water. But we learn now with climate change that it puts some pressure on the source, on the quality, on the quantity, and also on the awareness that actually sometimes we are, or most of the time, we are unintendedly reusing part of our water. We can find all the pharmaceuticals, all the industrial compounds there, so actually it's already there. But to make the next step requires something more. Well, what's that something more, and what's the context? We have this scheme. I'm a technologist, so I like schemes. With the isolate, the surface water, then there's conventional pretreatment, and then it will go into processed water for the drinking water in advanced oxidation with infiltration, or ultrafiltration reverse osmosis, or industrial processed water. And what we're aiming at here is, can we reach the same process water quality that you have after conventional treatment of the surface water in the same way using wastewater as a wastewater treatment plant effluent as a source? And it has two reasons. One, of course, you utilize and you have tailor-made water quality. But the other is more of societal aspect. When you show and illustrate what effort it takes to actually reach something such a surface water quality, conventional treatment quality, using wastewater, it learns you what effort you need to take care of your source protection. And that's also in the dynamics. We learned a few years ago in Netherlands, climate change really impacts the availability of water, and this is the priority sequencing by the Dutch water management. So you start with category 1 safety, and then there is the utilities, and the industry is at a lower scale. So now when there is pressure on sources, maybe you'll also lose some of your priority for industry supplies. Another reason, we're together with the Water Authority and the water company in North Holland, and actually 5 kilometers apart from each other, the Water Authority is plunging their treated, and the treatment is based on nutrient removal in the effluent in the IJssel Lake, and 5 kilometers downstream, the utility is taking it in as a source for drinking water, and of course you have all types of blending. But it is worthwhile to use this case study on how back and forth things are impacted. And for the authority, they have to focus on pharmaceuticals, they learn more about microplastics and antibiotic resistance. It's all same all over the world when you look at wastewater. And at the treatment plant, of course, compounds of concern are a continuous concern, and chloride levels or availability of water is a concern. So the ambition was, can we treat that wastewater for high reuse application, meeting that target that I mentioned, conventional surface water treatment. The reuse scenarios were, if you can't take the IJssel Lake, make exactly the same with wastewater treatment plant, advanced wastewater treatment, and then process water. And you should have a water quality that allows the current use of industry water, use as infiltration water, and potentially as pretreatment for reverse osmosis. It started, of course, with a period of shortage of fresh water and a broad range of micropollutants that we see. We're already since 2016 exploring this type of work. We've done quite some water quality assessments. It is not the silver bullet or the solution for everything, such a treatment, but it does help you to get insight in your water management and water cycle approach. So then again, a system, the outlook would be, we have the effluent ozone treatment for pharmaceutical reduction, but also for ceramic microfiltration performance enhancement, and inline coagulation for fouling mitigation and flux enhancement. This is our small pilot that we worked on. It's an everything pilot. It's almost a large bench scale type. And the ozonation conditions were ozone DOC ratio of 0.9 and ozone DOC ratio really high of 1.9. And looking at the coagulation dosage of 10 milligrams ferric as ferric at a pH just below the 7. So then, to keep the overview in technological results, we show the just the ceramic microfiltration on the effluent and what the flux behavior is, and then with the subsequent pretreatment. So first, we look here at over time 24-hour test just to get a feel for TMP increase at 3 fluxes, and with increasing fluxes you do see that it becomes less and less viable. TMP increases to levels that is no longer feasible. So then that's a good reference to compare that with inline coagulation and ceramic microfiltration. The advantage of ceramic microfiltration in combination with coagulation is that you can clean your ceramics very well with all types of chemicals. And here we see that the impact of the coagulation in combination with that ceramic has quite some positive effect on the flux, on the fouling behavior. If you look at ozonation and ceramic combination, that also allows a good stable operation, but it depends a bit on the ozone DOC ratio, so also on, I would say, residual of the ozone. That's what we see here. A higher ozone DOC ratio leads to more stable operation. All in all good, and then you put it all in line, and of course that works even more robust and stable. That's something to expect at substantial fluxes. If we look at water quality, because that's what the target is, we know from the conventional treatment that you have a UV transmittance of about 89%, and this is what we can also reach with the ozonation and the coagulation treatment, and that relates also a bit, not completely, to dissolved organic carbon. The other, that's the aim for the Water Authority, is the pharmaceutical degradation, and already at the ozone DOC ratio of 0.9, the bulk of the pharmaceuticals, everybody knows, is degraded and therefore removed from the system. But there's always a class that is not susceptible for OH radical oxidation or ozone oxidation, so that will remain there. Bromate formation, maybe not off topic in wastewater, but it's very much a topic in reuse, and even more in Netherlands. There is bromate guidelines for drinking water, and we also have them now for surface water. And we'd like to have that window. You're looking for maximum pharmaceutical degradation, and of course minimizing the bromate formation. And we learned that, of course, apply that in the wastewater. Adding the hydrogen peroxide to it will also mitigate or reduce your bromate formation. There is a window of control for the ozonation, and unfortunately in this graph on the horizontal axis it says ozone uptake, but you should divide it by 8 milligrams or 8 milligrams per liter of DOC to get the DOC, the ozone DOC ratio, and then you see till an ozone uptake of 10, which is 0.9 ozone DOC, you have no bromate formation. You can mitigate that, and making the peroxone process, so ozone hydrogen peroxide in red, you see you can continuously mitigate your bromate formation. Well, is that attractive for wastewater reuse? I'm not, for the operation of the membrane. That remains to be seen. Here you'd like to have no residual ozone to prevent bromate formation, but on the performance of the membrane, you may want to have a residual of ozone to enhance the flux. So that's where there is technological room for optimization. Also looked at other parameters, the antibiotic resistance, the bacteria, the virus, protozoa, all reported in a different work that we did together with KWR Water Cycle Research Institute, and the report is available online. So to conclude with this, wastewater treatment plant reuse, it is challenging. The DOC, the type of DOC, the ions, the PFAS, the ozonation byproducts, but advanced oxidation, can help to mitigate that. We did find a good pharmaceutical control with the ozonation. We could enhance the performance of the ceramic microfiltration in the combination with that ozonation. That really helps to produce the water, and also, and I'm not presenting, but that we did, helps the modified fouling index for the reverse osmosis to reduce this as well. So this would be really nice to feed into an RO system, given that maybe the fouling is something to, the biological fouling, biofouling would be something to look into, same as you experience. So both from an operational and water quality perspective, the combination of ozone and ceramic microfiltration, it is promising for a reuse system. You do have a robust system. You can apply all the chemicals on that. You have a fixed water quality coming out of that, that treatment that allows you for all types of reuse. And what we also learned is that this water quality really met the quality that we found in surface water and then conventional pretreatment. And then on the one hand you would say, wow, that's quite some technological effort to reach something simple as conventionally pretreated surface water. The other side of the coin is that with this research you illustrate what effort you really need to take before you discharge your wastewater. And you can always say, and that's what maybe wastewater treatment plants and water authorities may say, well, it's just a bit, I already improved it, I took the nutrients away, I reduced the pharmaceuticals. But for a utility taking surface water, that's not sufficient. You still need to do the effort for removal of the additional micropollutants, removal of the organic matter and the nutrients. So this is also a case study for that. I'd like to acknowledge the collaboration partners in this, of course, the utility, PWN, the water authority, which I have a very open relation with, and it's very good to have the water cycle approach, something that is new for Netherlands. IHE, Delft Research Institute, Dutch Ministry of Infrastructure and Water, a subsidy program, WETS, European Centre. So almost everybody worked with this together. And that's also the fun with closing a water cycle. You need to work with all the different entities in the water cycle and learn about one another's limitations, visions, ideas, and problems. And with that, I would thank you for your attention.